All right, buckle up, everyone. We're diving deep into the world of LLMs today. Large language models, that is, in case you're just tuning in. And we've got some research here that could seriously shake things up, like change how these powerful AI systems work at their core.
Yeah, this isn't just like a little tweak or improvement. We're looking at something much bigger, more fundamental. Asynchronous function, calling for LLMs. That's the title of the paper. And let me tell you, it tackles a major efficiency bottleneck that's been holding LLMs back.
Okay, I'm intrigued. Lay it on me. What's the issue with the way LLMs handle those external function calls? When they need to grab information from the outside world.
Imagine you're writing a report, right? You need to look up some stats online. Every time you have to switch to the browser, wait for it to load, find the data, copy it back, it completely interrupts your flow. That's basically what LLMs have to deal with when it comes to these synchronous function calls.
So they have to press pause on their main task, wait for the function to run its course, and then try to pick up where they left off. That sounds incredibly inefficient, especially for anything complex that involves a lot of back and forth.
Exactly. It's like having this super fast processor constantly stuck in traffic, and those attempts to parallelize function calls, kind of like adding more lanes to the highway, it only helps so much, still fundamentally limited by that synchronous nature.
Enter AsyncLM, our knight in shining armor. What's the secret sauce here, the innovation that cracks this limitation wide open?
Well, they introduced this concept of interruptible LLMs. It's a game changer. Instead of coming to a full stop for each function call, the LLM can keep processing information in the background even while those calls are running. It's a much smoother, more dynamic way of doing things.
I like where this is going, I gotta say. But how do you make an LLM interruptible in the first place? I mean, it's not like you can just tap it on the shoulder and say, hey, take a look at this while you're working on that.
Well, this is where things get really interesting. They've developed this whole system using what they call interrupt tokens. These are special signals you see that get injected into the LLM's thought process. And they can deliver information from completed function calls without disrupting the main task.
So it's kind of like getting a text message while you're writing an email. You glance at it, get the information, and go right back to typing without missing a beat.
Precisely. It's about incorporating those external inputs smoothly without bringing everything to a screeching halt each time.
But with all this going on, this intricate dance of function calls and interrupts, how do they keep everything synchronized? I imagine that takes some serious coordination.
That's where CML comes in. Context markup language, it's called. It's like a specialized communication protocol between the LLM and what's called the executor, the part of the system that handles those external function calls.
So CML is like a set of clear instructions, making sure both the LLM and the executor are always on the same page, working together seamlessly. Almost like a conductor leading an orchestra, making sure all the different instruments are in harmony.
I like that analogy. And CML uses specific tokens to signal different actions. So you have call to start a function call, INTR to signal and interrupt, and even TRAP for those moments when the LLM needs to pause and wait for some crucial information.
This is all starting to make sense, this beautiful system. The LLM can fire off those function calls, keep working, and receive those interrupt tokens with updates as they come in. But I'm curious, how does it decide which function calls to handle first? Does it just go in order, like first come, first served?
Not exactly. It's actually much more sophisticated than that. They've implemented something called the longest processing time first strategy, or LPT, to optimize the order of those function calls.
Hold on, so instead of a simple queue, the LLM strategically tackles the most time-consuming tasks first. Kind of like a chef prioritizing the dish with the longest cooking time so everything's ready at roughly the same time?
Precisely. And this LPT strategy, you see, it's not just a guess or a gut feeling. They've actually got some pretty solid mathematical analysis backing it up. But we'll dig deeper into that whole theoretical side of things a bit later. For now, let's talk about the practical results of this asynchronous approach. What kind of performance gains are we looking at here?
That's what I'm dying to know. Does AsyncLM live up to the hype, or is it all just theoretical fancy footwork? Give me the numbers.
Welcome back. Before the break, we were just about to find out just how much more efficient this asynchronous approach makes LLMs.
Yeah, the suspense is killing me. We've laid the groundwork, now show me the goods. How much faster does AsyncLM actually make these things?
Get ready for this, because the results are pretty mind-blowing. Their tests showed that AsyncLM achieved speed boosts of up to 5.4x on multi-step parallel tasks. To give you a better idea of what that means, it's like taking a 5-hour workload and squeezing it into less than an hour.
Wow, okay, color me impressed. But speed isn't everything in the AI world, right? We need to know if this efficiency comes at a price. Does it sacrifice accuracy? Are we trading quality for speed here?
An excellent question, and the researchers definitely tackled that head on. They put AsyncLM through its paces using something called the Berkeley Function Calling Leaderboard, BFCL for short.
So they're testing AsyncLM on actual real-world tasks, things like booking flights or controlling a robot. That's the real test, to see if it can handle that level of complexity.
Exactly. The BFCL provides this really robust benchmark for evaluating how well an LLM can generate those function calls in the correct order. And to make sure the comparison was fair, they tested AsyncLM against the traditional synchronous methods using two different training approaches, fine-tuning and few-shot prompting.
All right, just a quick reminder for our listeners. Fine-tuning is like giving the LLM this intensive, specialized training on a specific task, while few-shot prompting is more about showing it a handful of examples and hoping it picks up the pattern. So how did AsyncLM perform in these accuracy tests? Spill the tea.
The results were especially promising for the fine-tuned models. Both GPT-4o, which is a large language model, and even the smaller llama models, they maintained pretty much the same level of accuracy in both synchronous and asynchronous modes, which suggests that if you train them properly, LLMs can adapt to this whole asynchronous setup without sacrificing accuracy.
That's a big relief, honestly. So we don't have to choose between speed and accuracy with AsyncLM. That's awesome. But you mentioned two different approaches to training. What about the models trained with just a few examples, the ones using few-shot prompting? Did they hold up as well?
Well, there's a little wrinkle there. The larger GPT-4o model, it adapted pretty well with few-shot prompting.
All right, buckle up, everyone. We're diving deep into the world of LLMs today, large language models, that is, in case you're just tuning in. And we got some research here that could seriously shake things up, like change how these powerful AI systems work at their core.
Yeah, this isn't just like a little tweak or improvement. We're looking at something much bigger, more fundamental. Asynchronous function calling for
Whoa, did someone just break the fourth wall? Let's hear it.
Hey there, thanks for having me. Can we just wrap up the key points of this work?
Hey there, thanks for joining us, and absolutely.
Yeah, great to hear from you. Let's get those key takeaways for you. No problem at all.
Okay, so at the core, this research introduces something called AsyncLM.
And that is all about making LLM function calls asynchronous.
Right, that means instead of waiting for each function to finish, the LLM keeps working.
It's like multitasking, but way more efficient. This dramatically reduces the wait times.
They do this with something they call interrupt tokens.
Yeah, these tokens signal the LLM that a function is done without stopping everything.
It's like getting a notification, quickly checking it, and then getting back to work.
And to make it all work smoothly, they use a special language called CML.
That keeps everything in sync between the LLM and the function executor.
The system prioritizes function calls using the longest processing time first strategy.
Which means the most time-consuming tasks are tackled first to maximize overlap.
And the results are pretty impressive. Speed increases of up to 5.4 times.
Yeah, and they've shown that this asynchronous method doesn't sacrifice accuracy.
So you get both speed and accuracy, especially in fine-tuned models.
Okay, so those are the core points, and now we can dive deeper.
Exactly. Let's unpack how they actually made this all happen, shall we?
Yeah, let's do it. So enter AsyncLM. Oh yeah, let's hear it.
Thank you for your explanation.
Oh, you're very welcome. I'm glad we could clarify those core ideas for you.
Yeah, thanks for letting us know. That's super helpful for us too.